Hello, my name is Stanislav Musikhin. I'm a University of Waterloo PhD student in the group of Professor Kyle Dunn. My research topic is microwave plasma synthesis of graphene and its laser-optical in situ characterization. So we are interested in graphene because of its unique properties. It makes it suitable material for a wide range of applications, and some of them listed here. As a result, there is a demand for high-quality graphene in large quantities. One of the promising methods to produce high-quality graphene is gas-phase microwave plasma synthesis. That process can be continuous and scalable, and there is no need in a substrate. The problem is that the product yield is less than 5 weight%. Hence, the motivation of my study is to improve our understanding of the gas-phase graphene synthesis, so we can improve the efficiency of the process. And ex situ techniques such as transmission electron microscopy or Raman, they cannot help here. We want to see how graphene is being formed, what reactions are happening inside the reactor. And for that, we need in situ diagnostics, and that is my PhD topic. So this is a schematic of the synthesis process. We produce graphene from ethanol vapor using microwave plasma. Absolute ethanol is first atomized with argon and then evaporated. We introduced ethanol vapor into the quartz tube through a nozzle, where microwave radiation is focused and plasma is created. That plasma dissociates the ethanol molecules into smaller fragments, and then they reassemble into few layer graphene flakes. The quartz tube is installed inside the reactor, and what you can see here is thermal emission coming from hot graphene particles. So there are a few in situ optical diagnostics that we used. Laser-induced incandescents is one of them. This is a reactor top view. Graphene nanoparticles inside are heated by the laser pulse to the temperatures high enough so they start to incandesce. And then they return to the ambient temperatures through heat losses like sublimation and conduction. That emission that we detect during the cooling process contains a lot of useful information. We measured in situ particle concentrations, so now we can see online if we produce more particles or less particles. And at the same time, we can distinguish between graphene and soot because they interact with light differently and produce different signals. Another in situ technique we implemented was Fourier transform infrared spectroscopy. By shining the infrared light through the reactor, we can detect the gaseous species that are formed during the synthesis, and we can measure their concentrations. That information helps us to learn more about the chemical kinetics of the process. Alright, so these were just 2 examples, but there is so much more what we are working on and more interesting science to come.